Hello everyone, my name is Jitendra Seth from SRM University AP, India. I am doing PhD under the supervision of Dr. Manikandan BM. Today I am going to present our work. So the work title is Autoencoder Assisted Deep Spectral Learning for Hyperspectral Beveridge Classification. Next I'll talk about the what is hyperspectral imaging. Hyperspectral imaging is a powerful technology combining spectroscopy with imaging capability, and it enables gathering details information about the composition and characteristic of object and surface in a way that is impossible with conventional imaging system. And in forensic research, hyperspectral imaging has become a potential non-contact technique across hundreds of continuous band in the visible and near infrared spectrum. It records comprehensive spectral information at every pixel. In contrast to conventional RGB imaging, hyperspectral imaging make it possible to identify small spectral changes that are invisible to our naked eye. Because of these features, this character, it can identify chemically identical materials like dry beverage stain with great effectiveness. Next, I'll talk about application of hyperspectral imaging in terms of forensic science. So there are more application. So, but here we have listed a few application. So first one is detection of blood stain and body fluids. Second one is latent fingerprints. Third one is document examination. Fourth one is fever stain and age detection. Fifth one is gunshot residue analysis. Based on this application, we have focused on fever stain and age detection in this area because there is not much more research in this particular topic. So we have choose this area. Next, I'll talk about how does hyperspectral imaging work. So hyperspectral imaging does not just measure each pixel in the image, but also measure the reflection, emission, and observation of electromagnetic radiation. It provides unique spectral signature of every pixel, which can be used by processing technique to identify and discriminate the materials. So below the figure, you can see that hyperspectral image is giving more channels, more bands compared to RGB image. That is RGB image, we are getting only three channels, that is red, green, and blue. So and we are getting that spectral signature in terms of hyperspectral imaging, so that we will get much more information compared to RGB image. Next, I'll talk about how we will capture the hyperspectral image. So we have used Peking IQ, one company camera, that is we have used for our capturing our hyperspectral image. So the camera captured the spectral information in between 400 to 1000 nanometer wavelength, and the distance should be from camera to the light source and the sample, it should be minimum 15 centimeter, and it can beyond more than you can go beyond more than 15 centimeter, but minimum we need to follow 15 centimeter. The system records 3D data cube with two spatial dimensions and one spectral dimension, and each image contains 204 bands, and it generated the that size of that cube is 512 into 512 for 204 channels. So in below figure, you can see this is how we have captured the image. Two halogen light, one camera, and that proper distance we have maintained. We have given the wide reference also for reflectance purpose. So like this, we have we set up the process for capturing the hyperspectral image. Next, I'll talk about how we'll prepare the data. So we capture the hyperspectral image of Beveridge on three different tissue paper, that is white, pink, and brown. And we have studied 9 different Beveridge and the time duration is we have captured like from 0 minute to till 5 hours. Each hour we have captured the image, and the time duration is 1 hour gap is there, and we cropped and extracted the pixel values from the stain and stored them in a separate CSV file. And we have created 9 separate CSV file for all the beverage, and we mask them in a single CSV file for our implementation purpose. And below figure you can see that this is the sample of one white tissue paper, and we have marked all the beverage on this, and we have poured almost 0.5 milliliter to 1 milliliter that beverage amount we have poured in that tissue paper. Next, I'll talk about the spectral signature of different beverage. So first one is papaya beverage, spectral signature. Second one is coffee. Third one is pomegranate. So like this, we got spectral signature of all 9 beverage strain. So yes, from this plot, we observe that the average spectral signature of different beverage strain, each curve represent the reflectance value across the hyperspectral wavelength range. Although some beverage appear visually similar, their spectral pattern differs, particularly around 500 to 600 nanometer region. And this unique spectral characteristic provide discriminative features that enable accurate stain classification. And we have used 2 baseline model for our implementation. So that is MLP and 1D CNN. So this baseline model help us to understand how much improvement is gained from learning a compact spectral representation. And for proposed framework, we have our proposed framework combines unsupervised spectral representation, learning with supervised classification. First, a fully connected autoencoder compress the high dimensional hyperspectral spectra into a compact latent representation. Then these latent features are passed to a 1D CNN, like one dimensional CNN classifier, to perform beverage strain classification. So in below figure, you can see we have given one workflow diagram of our beverage strain classification. And next, I'll talk about the autoencoder and CNN learning. So the autoencoder reduces the dimensionality of spectral data by learning a compact latent representation. In our experiment, we have the data, the latent dimension was set to 64 because we have selected this 64, which preserve important spectral information while removing redundancy. And these latent features are then received and fed to 1D CNN, which learn spectral relationship and predict the final beverage classes. And now we'll talk about comparative study of different model. First one is MLP, classification report of MLP model. So here you can see the precision recall and F1 score of all the 9 beverage, similar for CNN model and AE plus CNN model also. So this classification report show that the proposed autoencoder plus CNN model improves precision recall and F1 score across most beverage classes compared to baseline models. Now we'll talk about the between model comparison between 3 models. So this bar chart, it compares the classification accuracy of 3 models, that is MLP and CNN and AE plus CNN. So the MLP model shows the lowest performance among the evaluated method. The CNN model improves accuracy by capturing spectral dependencies. The proposed model, that is AE plus CNN framework, achieves the highest accuracy, demonstrating the advantage of learning compact spectral representation before classification. And these are the confusion matrix of 3 models. First one is confusion matrix of MLP model. Second one is our proposed model, that is AE plus CNN. And third one is CNN, that is baseline confusion matrix. So this confusion matrix for the proposed AE plus CNN framework shows strong diagonal dominance indicating high classification accuracy. Most misclassification occurs between wine and pomegranate and between whiskey and rum due to similar spectral signature. And now I'll talk about the training and validation performance across different models. So in these two figures, we have plotted all three models. That is, first one is comparison of accuracy of three models, and second figure is the comparison of loss across all model. So here MLP shows slower convergence and lower final accuracy, and CNN converts faster but stop earlier due to early stopping. AE plus CNN achieve highest validation accuracy and stable the convergence. Training and validation loss here decrease constantly because it indicating the effective learning without serve overfitting. And now for conclusion feature work, we'll say that we have proposed an autoencoder based CNN framework for hyperspectral Wallenstein average stain classification. In this framework, effectively reduce spectral redundancy and improves class separability. In this experimental result demonstrate that the method achieved almost 96.9% classification accuracy, making it suitable for non-destructive forensic analysis. And for our future work, we plan to integrate spectral and spatial learning method to further improve classification performance. And we also aim to test the system in real forensic environment, including varying illumination condition and compound stain. And these are the reference we have followed for our work. Thank you.